So I'm just going to start with oxidation numbers because I think there's some confusion about the difference between oxidation numbers and formal charge. And that's totally understandable because we use a lot of the same rules for determining them, but some of them are different. And the basic rule is that we treat all atoms like they're ions, even if they're in covalent bonds. We just treat them like they're ions. And so whoever has the higher electronegativity, and here's a good time to have like a table, your electronegativity table in front of you. Although there's basically, the ones we're basically going to be dealing with a lot are oxygen, fluorine and chlorine, bromine, nitrogen, and phosphorus, and sulfur. Those are like the main ones we're going to be coming back to over and over and over. So those ones are going to change a lot, except for most. Fluorine basically is the same oxidation number all the time. Oxygen is the same oxidation number all the time, pretty much. But things like sulfur and phosphorus will change a lot. So I'll talk about how that works. So if an element is in its most stable state, in other words, oxygen, O2, hydrogen, H2, nitrogen, N2, fluorine, F2. If they're uncombined with other elements and just bonded to itself, then they have an oxidation number of 0. So like I said, O2, H2. Oxidation number of ions, like it's a simple ion, like here I got sodium, that's its oxidation number. So if calcium is +2, that's its oxidation number. If chloride ion is -1, that's its oxidation number, okay? Now, when we get compounds or polyatomic ions, when you add all of the oxidation numbers of the elements in that compound or in that ion, when you add them all up, the overall number that you add up is just the charge of the ion. And the example that's given here is sulfate ion. So how do we figure out what the oxidation numbers are for sulfate ion? Well, you start with oxygen. Oxygen is almost always going to be -2. Why? Because it's super electronegative. The only element that's more electronegative than oxygen is fluorine. So if oxygen is basically bound to anybody else, it's going to be stealing those electrons from the other element and claiming them for itself. So oxygen is almost always -2. So if oxygen's -2, and there's 4 of them, that's -8 so far. But sulfate with a charge of -2, all of the oxidation numbers have to add up to -2. So automatically we know that, well, sulfur must be +6 then. Because when we add up +6 and -8, we got to come out to -2. So within an ion, the most electronegative element has an oxidation number. That's what its oxidation number would be if it was an ion. And remember, oxide is -2. The oxide ion is -2. So if oxygen's bound to anything but itself or fluorine, its oxidation number is going to be -2 as well. So that's how we figure out, basically, when we're trying to figure out oxidation numbers for a compound or a compound ion, we figure out which ones we know, oxygen, fluorine, those, and then we use those to figure out what the other atoms are. In this instance, sulfur. So the sum of all the oxidation numbers in a neutral compound is going to be 0, right? Just like an ion, we add up all the oxidation numbers and it comes out to the charge. Well, a neutral compound has a total charge of nothing. And so the total oxidation number has to be 0 when you add them all together. So here we have FeO. Oh, here we have iron. Iron 3 oxide. How do we know it's iron 3 oxide? Well, because we know that oxide ion is -2. There's 2 irons. So if we have a -6 for the oxygens, we got to have a +6 for the irons, because they have to add up to 0. And that leads to another point. If you see Roman numerals, that's an oxidation number. So iron 3 oxide tells us that that's +3. Copper 2 sulfate tells us that's +2. So you don't have to do any thinking on that one. If you see a Roman numeral, you automatically know what the oxidation number for that particular metal is. So hydrogen. Hydrogen is almost always +1, because if it's in a compound with a nonmetal, then the nonmetal is going to have a higher electronegativity than hydrogen, pretty much any nonmetal. So chlorine, fluorine, oxygen, sulfur, any of them. So hydrogen only has the single electron. So when it donates its single electron, then it's +1. The only time it isn't is when it's bound to a metal. And when hydrogen's bound to a metal, it becomes a nonmetal. And it has a higher electronegativity than most metals. So if it's in a metal hydride, like sodium hydride, sodium is going to be +1 when it's an ion, and hydrogen is going to be -1. But that's fairly rare. Like 95% of the time, hydrogen is going to be +1. Then we come to oxygen. Almost always -2. And there's really only 2 exceptions to that rule. One is when it's in a peroxide compound. And a peroxide compound is when oxygen is bound to itself and another element, like hydrogen, for instance. This is hydrogen peroxide. Probably familiar with hydrogen peroxide. So if we look at the electrons around the oxygen, so each oxygen can steal an electron from hydrogen. So it steals these 2 electrons. The other oxygen steals those 2 electrons, but it can't steal an electron from itself. So it has 1, 2, 3, 4, 5, 6, and there's 2 electrons here, and they share that one because they have equal electronegativity. That gives them both 7. So oxygen normally has 6 electrons, it has 7 electrons, and so in that instance, its oxidation number is -1. The only other time it isn't -2 is, like I said, when it's bound to fluorine. So if we have this, we have oxygen difluoride, then you can see that both of the bonds, both of the pairs of electrons shared with fluorine go to the fluorine. These go to that fluorine, these go to that fluorine, and that oxygen is now only left with 4 electrons. So now, instead of 6, it's only got 4, and so its oxidation number is +2. That's the only time oxygen is positive. All the rest of the time it's negative, because it's so electronegative. So what I was going to do now, is there any questions about the oxidation numbers? So I was going to go into balancing redox reactions now. Does everyone have a fairly good idea? I mean, I'll talk a little bit more about it when we're balancing the redox reactions, because the very first thing you need to do when you're balancing a redox reaction is to figure out what all the oxidation numbers are. So that'll come back up again. So these are the basic steps, and you can see there's a lot of steps for doing these. So that's why it gets a little complicated. So very, very first thing you do, determine all the oxidation numbers. So for all of the, you determine all the oxidation numbers for all the elements in your reaction. And then you split them into 2 reactions. One would be the oxidation, where an element is increasing its oxidation number from going from reactant to product, and the reduction reaction, where an element decreases its oxidation number. That's why we call it a reduction. Its oxidation number is reduced. So it goes down between being a reactant and being a product. Then, once we have our two reactions, we balance all the elements other than hydrogen and oxygen, because we'll get to those later. So if we have one copper on one side and two coppers on the other side, we balance those out. Then we figure out how many electrons are involved. So if one element increases its oxidation number from 0 to, like, say, +5, that means it's lost 5 electrons. And so we put 5 electrons on the product side because it's lost them. They're gone from the reactant and they become products. Same thing on the other side. For the reduction side, how many electrons were added to that element? If an element went from +4 to 0, that element gained 4 electrons. And so we put 4 electrons in the reactant side because it added those electrons and then became a product. Now, if we have an acidic environment, we will tell you when we're balancing these, whether it's going to be in a basic environment, and in a basic environment, which ion is going to be present in high concentrations in a basic environment. Which ion are you going to find a lot of in a basic environment?
Hydroxide?
Exactly, yeah, hydroxide ion. There's going to be a surplus. I mean, that's why it's a basic environment. There is a surplus of hydroxide ions. So we use those to balance the charges. What about if we're in an acidic environment? Which ion is going to be in a surplus then?
Hydrogen.
Not hydrogen. You're close. It's charged, remember.
Hydrogen ion?
Mm-hmm. H plus. In an acidic environment, you have an excess of H plus. So we use H plus to balance the charge. Because remember, in any reaction, we have to balance a lot of things. We have to balance the atoms, have to be the same on both sides. The charge has to be the same on both sides. And the number of electrons have to be the same on both sides. Everything has to balance. So we balance the charge on both sides by adding H plus when they're in excess in an acidic environment, or OH minus when they're in excess in a basic environment. Now remember, the charge is not always going to be 0. Sometimes it might be +2 on both sides, or it might be -3 on both sides, but it just has to be the same on both sides. So then we add water to balance out the number of hydrogens and oxygens. We add water wherever we need to. If there's excess hydrogen on one side, we put water on the other side to balance out the hydrogen. Generally, that will balance out the oxygen at the same time. Then we have to balance the electrons. So if we have 5 electrons going in, but only 4 electrons coming out, we need to balance that to make sure that they're exactly the same. So we would multiply one of the reactions by 4 and one of the other reactions by 5, so there would be 20 electrons on both sides, 20 electrons going in, 20 electrons coming out. Then we add the two equations together. We have our oxidation reaction, we have our reduction reaction, we add them all together. And there's going to be a lot of duplicate terms. There's going to be duplicate protons, there's going to be duplicate hydroxide ions, there's going to be duplicate waters, and we cancel them out wherever we see the same thing on both sides. Okay? It'll be a little more clear, hopefully, when we do one of these. So just like I said, in acid, you balance the charge by using protons. In base, you add hydroxide ions. And every time you add a hydroxide ion to one side, you add a water to the other side. That balances out the oxygens. So here's an example. So we got a reaction right here. And so we have copper sulfide plus nitrate ion. We put those two together and a redox reaction takes place. Copper sulfate or copper sulfide, we now have copper 2 plus becomes an aqueous ion. Sulfate is released as an aqueous ion, and nitrogen monoxide is released as a gas. So first thing we need to do is work out what the oxidation numbers are, okay? So very first thing, we look and see how we can figure out what the oxidation numbers are. So what is the charge on sulfur when it's a sulfide ion? Because we don't know what the copper could be 1 or it could be 2. So we don't know what the redox, we don't know what the oxidation number of copper is. We need to figure it out by figuring out what is the oxidation number of sulfide ion. So what's the charge on sulfide ion?
-2.
Mm-hmm. It's in group 6. It's just below oxygen. So oxygen's always -2. And when sulfide is an ion, it's -2 as well. So we automatically know that the sulfur has an oxidation number of -2. Now remember, this is an ionic compound. So both the copper and the sulfur are going to be charged because it's a metal and a non-metal. So if we figure out what the charge is on the sulfur, and we know it's -2, we automatically now know that the charge on the copper must be -2 as well. Now, when it comes to the nitrate, we use the rules we sort of learned about oxygen just a minute ago. So we have nitrogen and 1, 2, 3 oxygens around it. So it's bound to 3 different oxygens. So what are the oxidation numbers of the oxygen? Since it's not bound to itself and it's not bound to fluorine, what's its oxidation number going to be?
-2.
Yeah, it's got to be -2. They're all -2, -2, -2, -2. The overall charge of this polyatomic ion is -1. So I already have -6 for the oxygens, and the total is -1. So what has to be the oxidation number of the nitrogen?
+5.
+5 -5
Of the nitrogen?
for the nitrogen.
Plus.
Plus, yeah. When you're talking about oxidation numbers, you always have to have plus or minus in front of them. So +5. So we know that the nitrogen is +5, oxygen's -2. Now, that's on the product side. I'm sorry, on the reactant side. Now we look at the products. So copper is an ion. So bingo, we already know what its oxidation number is. It's -2, or sorry, it's +2, because that's what its charge is. Now, sulfate, that's going to be a little tricky to figure out. We have to, again, use the rules we learned earlier. So we've got sulfur and 1, 2, 3, 4 oxygens bound to it. Now, again, oxygen's not bound to itself, and it's not bound to fluorine, so what must its oxidation number be?
-2.
Still -2. -2, -2, -2, -2. So we've got -8 now for oxygens. The overall charge of a sulfate ion is -2. So what must the oxidation number of sulfur be in the middle?
+6.
Mm-hmm. It's got to be +6 because we add up -8 and +6 and we get -2. So we know the sulfur is +6. Now, we have nitrogen monoxide. So nitrogen monoxide, they're both nonmetals. So this is a covalent compound. But again, oxygen is bound to something that isn't itself, and it's not fluorine, it's not fluorine. So the oxidation number of the oxygen, again, has to be -2. So if oxygen is -2, what does nitrogen have to be?
+2.
It's got to be +2, right? Because it's not a charged species. It's a neutral molecule. So nitrogen has to be +2. So then we get, so that's first step, get all the oxidation numbers down. So then we see who's getting oxidized and who's getting reduced. And so we can see that nothing's happening to the copper. It was +2 over here, and it's +2 over here. So it's not being oxidized or reduced. So it is not involved in the oxidation reduction reaction. Sulfur went from -2 to +6. That's a serious oxidation. So it lost 8 electrons. So it was -2, it was up 2, and now it's down 6. So it lost 8 electrons. It has seriously been oxidized. And you can tell it's been oxidized because look who it was bound to before. It was bound to a metal. So metals like to give electrons away. And now it's bound to oxygen. Now what does oxygen do? It steals electrons, and it's got 4 of them, stealing 2 electrons each. That's 8 electrons, right? So that's the oxidation reaction. The reduction reaction, oxygen doesn't change its oxidation number. It was -2 when it was bound to nitrate, and it's -2 when it's bound to nitrogen again. But notice the difference. Nitrogen was bound to 3 oxygens as a reactant, and on the right side, it's only bound to 1. And so its oxidation, it's gone down. It has actually been reduced. With fewer oxygens bound to it, it's been reduced. It's gone from +5 to +2. So it has gained 3 electrons. So this is our oxidation reaction, and this is our reduction reaction. Now we have to start balancing stuff. So we have to balance elements other than hydrogen and oxygen. We save that to the end. And so we see we've got 1 copper on this side, 1 copper on that side, 1 nitrogen on this side, 1 nitrogen on that side, 1 sulfur, 1 sulfur. So we're good. We don't have to balance any of the other elements. So we're good there. Move to the next step. We have to figure out how many electrons are involved in our oxidation and our reduction. So like I said, sulfur is the one being oxidized. It went from -2 to +6. That's a total of 8 electrons that it lost. And so that is a product, because when it loses the electrons, they go away, they go somewhere else. So they go on the product side. So we have to add 8 electrons on the product side. Now nitrogen went from +5 to +2. Its oxidation number was reduced by 3. What does that mean? It gained 3 electrons. So we put 3 electrons on the reactant side. So now we have the right number of electrons going in and coming out. Here you would figure out whether it's an acidic environment or a basic environment. And any redox reaction, we have to tell you that. It has to be in the question, or else you won't know what to do. So usually in the very first part of the redox reaction, say balance this redox reaction in an acidic environment, or balance this reaction in a basic environment. This is an acidic environment, so we add protons or H+ ions where we need them. So we need to balance out the charges. So on the oxidation reaction, on the reactant side, there's no charge. So there has to be no charge on the product side. So we've got +2, -2. So those two balance. We got -8 for our 8 electrons. So we need 8 protons. So we have 0 charge on this side, 0 charge on that side. Now we look at the reduction reaction. We have a -1 here, and we have -3 for the 3 electrons. There's no charge on this side, so we need 4 protons to give us no charge on this side, no charge on that side. So now we've balanced our charge on both sides. Next, I told you there's a lot of steps to these. Now we balance the hydrogens by putting water in. So I have got 8 protons in my oxidation reaction. So to balance that out, I put 4 waters, because there's in 4 waters there is 8 hydrogen atoms. So that balances out my hydrogen atoms. On the reduction side, I had 4 hydrogen ions, so I need 2 waters on the other side to balance out my hydrogens. So far, so good. You see, we haven't balanced everything yet, but we're getting there, slowly making our way.
Can I ask a question?
Oh, go ahead.
So how come you added the minus sign from NO3 to the 3 electrons, but then you
Because
didn't
it's a charge.
But what about the -2 on SO4?
That is balanced by the copper is +2. And
Oh,
the sulfate's -2. So those two add up to 0.
okay.
Yeah.
Thank you.
No problem. Yeah, so any negative charge or positive charge, doesn't matter where it comes from. If it comes from an ion, if it comes, well, obviously it comes from an ion. If it comes from like hydroxide ion, or if it comes from nitrate ion, or wherever it comes from, we need to take it into consideration. So now we've got our hydrogens balanced. And like I said, that usually balances oxygens too. If it doesn't, we've probably done something wrong. Because remember, all these reactions are taking place in an aqueous environment, right? So an acidic and aqueous environment just means there's going to be more protons than hydroxide ions, but there's going to be a ton of water around, and water is going to get involved in the reaction as well. So now we need to balance our electrons, because with one reaction we had 8, remember, and the other one we only had 3. So we have to figure out what do we multiply both of them by to get the, basically we're looking for the least common multiple, I think, right? Least common multiple. So we get the same number on each side. So 3 and 8, really like the only things we can do is multiply one by 3 and the other by 8. So we had 8 electrons in the oxidation. We had 3 electrons in the reduction. So we multiply the oxidation by 3 and we multiply the reduction by 8. That way we have 24 electrons as reactants, and we have 24 electrons as products as well. So that balances everything. Balances the electrons. Then we add them both together. So we take our oxidation and our reduction. We put all the reactants on one side, we put all the products on the other side. And then we just start canceling out what's the same on both sides. So you can see that we've got a lot of protons on both sides. We had 24 as products, and we have 32 of them as reactants. So we have a net of 8 as reactants. We had 12 waters as reactants, and we had 16 waters as products. So we cancel those out, and we have a net of 4 waters as products. The electrons cancel out, which they should. And then what we're left with is, this is our final reaction. So 3 copper sulfates plus 8 nitrate ions plus 8 protons make 3 copper ions, 3 sulfate ions, 8 nitrogen monoxides, and 4 waters. So we should have, everything should be balanced. We should have the same number of coppers on both sides. We do, 3 and 3. We should have the same number of nitrogens, 8 and 8. We should have the same number of hydrogens, 8 and 8. And the same number of sulfurs, 3 and 3. And the same number of oxygens. We've got 24 on this side, and we have 12 plus 8 plus 4, 24. The other thing that should balance as well, this is like the last thing you should check, is is the charge the same on both sides? If the charge is also the same on both sides, then you've got it. So let's check if the charge is the same on both sides. I've got -8 here, +8 there for 0. And on the other side, I've got +6, -6, 0, 0. So yes, there's no charge on either side. But like I mentioned before, there may be a charge on both sides. There may be -2 on both sides, or +2 on both sides, or -6 on both sides. But it has to be the same on both sides. Whatever the charge was going into the reaction has to be the same as the charge coming out. But that should be the last thing you do, like when you're doing a test or something. Make sure your overall charge balances on both sides. Then you pretty much be guaranteed you did that correctly. All right. So any questions on that? I figured I would do one more. I would do the basic balancing with you and then let you get started. Any questions about the acidic balancing?
I have a question.
Yep. All right.
So if any of those don't balance, you're going to want to redo the entire thing, right?
Yeah, go back. Yeah, because something must have gone wrong. So just go back. And the usual thing is that you got one of the oxidation numbers wrong. That's the usual thing. So if either your oxygen or your hydrogen is not out of balance, you probably got one of the oxidation numbers wrong. If, for instance, the copper is not balanced, you probably just, forgot to balance the non-hydrogens and oxygens at the beginning. But yeah, just go back and double check. First thing to double check would be, are my oxidation numbers all correct? Yeah, that's why, yeah, there's a lot of steps. So that's why these problems take so damn long when you're doing a test. That's why I always leave these till the end. Do the easy ones first and then come back to balancing redox reactions, because those will take they take me a long time to do anyway. Some of you may be like super geniuses and be able to do them pretty quickly. Right, so the first question was balancing a redox in acidic aqueous solution. I sort of went through how to do that. So I was going to skip this one, let you do that, work on that one on your own, and do the basic aqueous solution. So let's start with figuring out what our oxidation numbers are. So we have bromate ion, we have solid iron, and then we get bromide ion and iron 3 ion as products. So what is the oxidation number of the iron here?
Zero.
Yeah, 0, right? Because it's all by itself. It's just a bar of iron or a lump of iron. So the only thing it's bound to is itself. And so anything that's just bound to itself and nothing else, its oxidation number is 0. So what's the oxidation number of iron as a product?
+3.
Yeah, it's an ion, the +3. It's all by itself. So it has to be +3. Now let's look at the others. What is the oxidation number of, I've got my bromide ion. So what is, or bromate ion, what is the oxidation number of bromine here?
+1.
Ooh, how'd you figure that out though?
Because the oxygen is -2, and then
There
the
you go.
overall thing is -1.
Right. There's no way to know what the oxidation number of bromine is until you figure out what the oxidation number of the oxygen is. And oxygen is bound to something other than itself, so it's going to be -2. And if that's the case, bromine's got to be +1, because when you add the two of them together, you get -1, because that's the charge. So now we have, we have one left. So we have +1 and -2. What's the oxidation number of bromine when it's a bromide ion? So here's our bromide ion. What's the oxidation number of bromine when it's a bromide ion?
-1.
Mm-hmm. It's all by its lonesome and has a charge of -1. That is its oxidation number. So who's getting oxidized and who's getting reduced?
Iron is getting oxidized.
Mm-hmm. So iron, oops. There we go. Yeah, so iron is going from 0 to +3. It is being oxidized. Who's being reduced?
The bromine.
Bromine's being reduced, right? Because bromine is going from +1 and its oxidation number is being reduced to -1. So have you been explained what reducing agents and oxidizing agents are?
Isn't it just the opposite?
Yes, basically it's the opposite. Whoever gets oxidized, think of it this way: whoever is getting oxidized is giving up its electrons so that something else is being reduced. So it's a reducing agent, because without it, the reduction doesn't take place. Unless someone gets oxidized and has its electrons stolen, nobody else ain't getting them, right? So whoever's being oxidized is the reducing agent. It's allowing reduction to take place. And the same is the other way around. Whoever's being reduced is getting oxidation to take place. It's oxygen, right? Because oxygen is stealing electrons from everybody. But you see here, oxygen's oxidation number isn't changing. We don't even have oxygen as a product. So it's bromine that's being reduced. And so bromine is stealing electrons from somebody. So it is the oxidizing agent. Who's the reducing agent?
Iron.
Iron, right. And you'll find that metals are usually the reducing agent, because what do metals do? They give up electrons. That's what they do. And so they usually are the reducing agent. And non-metals are generally the oxidizing agent. The reducing agent generally has a lower electronegativity. The oxidizing agent, not surprisingly, has a higher electronegativity. So let's work on balancing this thing. Figure this out. All right, so here's our reaction. We've already figured out what our oxidation numbers are. So we've got +1, -2, 0, -1, and +3. So the first thing we want to do is write out what's our oxidation reaction. So what is our oxidation reaction?
Fe to Fe3+.
That's right. This is our oxidation reaction. Fe on one side, Fe3+ on the other side. That's our oxidation. What's our reduction?
BrO- to Br-.
Mm-hmm. That's our reduction. So then we have to figure out how many electrons are involved. So where do we put electrons? The oxidation, where do we put electrons? Are they products or are they reactants?
The product.
They're products, right? They're being taken from somebody. So they're going to be products, exactly. So how many electrons in the oxidation reaction?
At 3 electrons.
Right, 3. So there's 3 more electrons as products. What about the reduction side? How many electrons on the reduction side?
Two.
Excellent. Right, because it went from +1 to -1. That's a change in oxidation number of 2. So we have to add 2 electrons on the reactant side. So next, we want to put hydroxide ions to balance our charge. So on the oxidation side, do we need any hydroxide ions to balance charge?
Is it already balanced?
It's already balanced, right? There's no charge on iron's not charged, and iron +3 and 3 negative electrons equals 0. So we don't need them for the oxidation. What about the reduction? Do we need any in the reduction side?
Is it 3?
Where do we put them?
On the product side.
Okay, 3. Add up the charges. So how much? What's the total charge on the product side, on the reactant sides, or on the left?
3.
-3. So what's the charge on the right now?
-4.
Ooh, so
So it would be 2 instead
2, right? So we need only 2. So we'll change that to a 2. So now let me actually move these a little bit. I'm going to need some room. So I've got +2 electrons, and I've got my ion +2 hydroxides. So since I put 2 hydroxides on the right side, I now need to balance my oxygens. So I've got 2. For every hydroxide, I put basically 2 waters on the other side. Actually, no, I just need 1 because I have two oxygens on the right. I only need one on the left. So my hydrogens are balanced. So I have two. My oxygens are balanced, 1, 1. Okay, so now we make sure that all of our atoms are balanced. So I have 1 iron, 1 iron. That's good. I have 1 bromine, 1 bromine. That's good. I have 2 hydrogens, 1 oxygen, 1 oxygen. So it seems all the atoms are balanced. So what's the last thing we need to balance?
Can I ask a question?
Oh, sure.
So when you have the hydroxides, you add the water to the opposite side,
Right.
and that's the same
To
for
balance the hydrogens and the oxygens you've just added.
that's the same for the when you have H plus, you add it to the opposite side.
You with the H plus, you add waters when you need them to balance out hydrogens and oxygens. That's right. It's the
Okay.
same. It's the same rule.
Okay.
Yeah, you add water. So if I added a bunch of protons to one side, I have to add waters to the other side to balance out the number of hydrogen atoms. So it's the same thing.
Okay.
The exact same thing, except the only difference is instead of balancing charge with H plus, when it's an acid, in a base, I'm just adding OH minus. Other than that, we're doing exactly the same thing.
Okay. Thank you.
No problem. Yeah, these things are complex. I get screwed up on them all the time. So my irons are balanced, my bromines are balanced, my oxygens and my hydrogens, the charges are balanced. One thing's out of balance. What's that?
Should it be 2 bromide?
Why?
Because the hydrogen on the left cancels out the hydrogen charge on the right. So then on the left you have -2, and on the right you have -1.
No, I have -3 on both sides. This is -1. This is -2. This is -1. This is -2. So they're -3 on both sides.
Oh,
Are you canceling out the 2e minus
What's the E minus? What's that?
electrons?
Electrons. We haven't balanced our electrons yet. Right, so we need to balance our electrons. So how are we going to do that? So now we have to multiply the entire reaction by something to balance out my electrons, because I need to have the same number going into the reaction as they're coming out. And right now I've got 2 electrons going in, but I got 3 electrons coming out. So that's not balanced. So how am I going to balance those?
You can multiply the oxidation reaction by 2 and multiply the reduction reaction by 3, so that but each one will have 6 electrons that you can cancel out.
Exactly. Excellent. Yeah. So now I will have 2 irons on both sides and 6 electrons. I will have 3 bromines, 6 electrons, 6 waters. Let me erase that. 6 waters, 3 bromide ions, and 6 hydroxide ions. So now I've got 6 electrons going in, I get 6 electrons coming out. So the last thing I do then is add everything together. So everything that's on one side of the reaction, I add together. So I have, so 2 Fe plus 3 Br minus plus 6 electrons plus 6 waters make 2 Fe plus 3, 6 electrons, 3 bromide ions and 6 hydroxide ions. Now I cancel what's the same on both sides. So what can I cancel on both sides?
How did you get 6 waters? Did you?
Oh, because I had 2, and then I multiplied the whole thing by 3, so I balanced my electrons.
But I thought there was originally only 1 water.
Oh,
Yeah, yeah, well, yeah,
you are right. Man, nice catch. So I should have only 3. Yeah, that would have not balanced then. Excellent. Okay, nice work. All right, so what can I cancel on both sides?
the 6 electrons.
Yeah, and if my electrons don't balance, this has been a huge waste of time. Yeah, so 6 electrons are gone. Anything else I can cancel out? Looks like that's about it, right?
Pretty much.
I've only got water on one side, so I think that's it.
So we're not going to balance the iron since the charge is different.
Iron is balanced. There's 2 iron atoms on one side, and there's 2 iron atoms on the other side.
Oh, we don't take that out.
Hmm?
We don't take that out.
Why? No, because they're different. One is an atom, the other is an ion. That's the whole point, is that the 2 iron atoms were oxidized into ions. That's the oxidation reaction. So it's not the same thing. We have Fe with no charge on one side, and we have Fe with +3 on the other.
Yeah, yeah.
So they're not the same thing. We just have to have the same number of them. But what's the last thing we want to check to make sure we've done this correctly? So we've balanced our atoms. Those seem to balance. We balanced our electrons, so that's good. What's the last thing we do before we call it a day?
Check the overall charges.
Bingo. Man, guys are sharp as a tack today. Right, so what is my overall charge of my reactants? So everything on this side. What's my overall charge here?
-3.
Yep, -3. Now what's the overall charge of everything on this side?
-3.
Product side.
-3.
-3, right. So I have +6 from the 3 irons. I have -6 from the 6 hydroxide ions, and I have -3 from my 3 bromide ions for a total of -3. So I have -3 on one side, I have -3 on the other side. So we've balanced everything. So we did it, people. We balanced the whole darn thing.